Hello everyone, my name is Dr. Vile and welcome to my A-Level Chemistry YouTube channel. The purpose of this channel is all about getting you ready for your A-Level Chemistry exams. And this video is going to focus in on an A2 topic in kinetics, which looks at something called the Arrhenius Equation, and it's all about the link between temperature and the rate constant. And we're going to explain what this equation is, all the different terms that are in it, and then use it to solve problems. So if you find this video helpful, please like, subscribe, share with your friends, and please keep checking back for more content which we're adding regularly. Particular exam paper, you were given the equation, but you won't necessarily be given the equation, so you do need to learn it. Some questions give it to you, some questions don't. Let's firstly just go through and look at all the different terms so we know what they mean. K is your rate constant. So the purpose of the Arrhenius equation, I suppose, is that you would calculate the rate constant at different temperatures. It's to see how the rate constant changes with temperature. The general principle is higher the temperature, the higher the rate constant. But it also, they are linked together by the activation energy, which we're going to get to. So K is your rate constant. The units of the rate constant will depend on the question, as we know. The rate constant unit is variable. So when you have a calculation like this, K is your rate constant, and it says that K equals A. Now, A is something called your pre-exponential factor. And we don't really need to know very much about it. From our point of view, it is just a number that we might need to calculate to solve a problem. The units of the pre-exponential factor are the same as the rate constant if it matters for the question. Okay, but normally we can treat A as just a number that we're trying to calculate. Then you've got this little E here. E is just a button on your calculator. It's a mathematical term. To access E on your calculator, you press Shift if you're using Casio, and then natural log, and that'll bring up the E button on a Casio calculator. So it's a mathematical function. And then you've got EA, which is your activation energy. Now, can I draw your attention to the units here? The activation energy, when you get a question, is normally in kilojoules per mole. So here you've got an activation energy of 79.333 kilojoules per mole. However, the gas constant R is in joules per mole. So we normally have to convert our activation energy into joules per mole before we can use the equation. Okay, so just be aware of the discrepancy of the units. R is the gas constant, and it is just on your table, on your data sheet, sorry. So the gas constant. And then T is the temperature, which needs to be in Kelvin. So if the data gives you degrees Celsius, you'd need to convert it into Kelvin first. Okay, so that's all the different terms of the equation. Let's look a little bit at the question we've got now. We've got a question where they've given you the rate constant at two different temperatures. So you've got a rate constant at 288 Kelvin, and then you've got a rate constant at 300 Kelvin. It tells you the activation energy, 79.333 kilojoules per mole. And the question asks you to calculate the rate constant at a new temperature of 295 Kelvin. First thing to note, 295 is roughly halfway between these two temperatures here. So you'd expect your rate constant to be somewhere in between these two numbers. If you get a number that is somewhere completely wacky and completely different, you've probably gone wrong. So it's a good excuse to go back and check. Okay, so you're expecting your answer to fall somewhere between these two numbers. So to tackle a problem like this, you're going to take your Arrhenius equation and you're going to rearrange it, firstly to calculate the value for A. Because once you know the value for A, then we can solve problems. But we need to know A, because it's the only thing that we don't know at the moment. So we need to rearrange this equation to make A the subject. You can actually think of this as three terms. If I just write it out here, K equals A times e to the minus EA over RT. You could effectively think of it as three terms. If I get the highlighter out, K is one of the terms, A is another term, and then e to the minus EA over RT is the third term. So it makes rearranging it actually pretty straightforward. Because what we do is we divide both sides by e to the minus EA over RT. And therefore our new equation is A, let's do that in black, A equals K divided by e to the minus EA over RT. So we've just rearranged it at this stage. Possibly a mark for doing that, just for rearranging the equation. Now at this stage we need to plug some numbers into the equation to work out what A is. It doesn't matter which of these two reactions you use, as long as you just stick to one of them. So I'll just go with the 288 Kelvin and the 0.0761, because in theory the pre-exponential factor doesn't change. So we start plugging our numbers in now. So K is 0.0761, and then E to the minus, well, the activation energy becomes 79,333 divided by 8.31, which is your gas constant, you just look it up on the data sheet, times the temperature of 288. And I get that to be, to three significant figures, 1.89 times 10 to the power of 13. But I would leave that answer in your calculator for the next bit and round at the end, but I've written it down there to three significant figures. So once you've calculated A, we're literally going to go back to our original equation and we're going to plug the numbers in to calculate K at the new temperature. So we'd say that K equals the 1.89 times 10 to the power of 13, but remember, leave it in your calculator if you can, times e to the minus, the activation energy hasn't changed, it's still 79,333. The gas constant hasn't changed, 8.31, but the temperature is now 295. And when I plug that into the calculator, I get my answer to be 0.167. We're not concerned with units because there's none given in the table. And I'm happy with that answer because it is pretty much bang on in between the two numbers there. So I'm confident that I've done something right at least. Okay, so hopefully that's helpful on how to use the Arrhenius equation to solve problems. This is quite a typical exam question where they get you to calculate it at the value for K at a different temperature using the data that's already given. And you'd firstly calculate A and then work out K at the new temperature. One other variation on the Arrhenius equation that you might need to do for the exam is to calculate the activation energy, which is a bit of a weird rearrangement. So if we know that K equals A times e to the minus EA over RT, and you want to calculate EA, you'd firstly divide both sides by A, so you'd say that K over A equals e to the minus EA over RT. And we need to get rid of this e term from the equation. Well, the opposite of that is the natural log. So we take the natural log of both sides. So you then have the natural log of K over A equals minus EA over RT. And at this stage, the natural log of K over A is just a number. RT is just a number because it's temperature times the gas constant, and therefore you could calculate what EA is. Okay, so that's just another variation on that type of question. Anyway, thank you for taking the time to watch this video. I hope it was helpful. If it was, please remember to like, subscribe, share, and keep checking back for more content. And I will see you next time. Thank you, everyone. Bye-bye.